welcome. Thank you very much. It's a very select and group this afternoon. The most important people in the conference are here, so thank you very much for coming. Let me kick off. And as mentioned, my colleague Taryn, who was due to present this, is not feeling too well, so I've stepped in on his behalf. I shall do my best to get through things speedily. Just a quick mention about the Chartered Institute of Ergonomics and Human Factors. This is the group that represents human factors professionals, and we, within the last few years, have achieved chartered status, so that means we are chartered human factors engineers alongside any other type of chartered engineer, which helps very much in terms of raising the profile of the discipline. I'd urge people to take a look at our website and join as members if you are interested in human factors or ergonomics. Anyway, let me get on with the presentation. What I was already mentioned about a bit about our organisation, we work mostly in oil and gas and have worked on globally over 100 oil and gas capital projects providing the human factors input. So all different types of projects, all different types of environments. And so we've got a very good idea on what it takes to be successful in terms of getting human factors into a project and building it in from the start, because we've all seen the problems that come to bear when we don't think about this when we design and build an asset, and we live with the problems for years to come. What we've been doing is trying to design those problems out. I mean, just a few examples. That's I think that's the Lekware asset PDO in the Oman Desert. That one's the Shell Prelude floating LNG, the biggest ship in the world. You can see how big it is. And huge human factors issues related to that. Brand new technology, never been used offshore before. It's in a typhoon alley and has very long manning tours of duty. So imagine what the human factors issues related to that design of that brand new type of asset were. We supported that project all the way through to construction. That's one that's ongoing at the moment in the North Sea, the Statoil Johan Sverdrup. That's going to be the biggest asset in the North Sea when it comes to operate. That's Kazan project in the Oman Desert, gas plant that we're currently working on. We've got the Pearl GTL in the bottom corner there, and the BP Glenline FPSO. That's the largest FPSO ever built. Just started operating in the North Atlantic. And this one in particular, this is the Kashagan asset in the Caspian Sea. The human factors issues related to that were enormous. As you can see by the photographs, it ranges from -40 to +40 degrees in terms of ambient temperature. The gas that comes out of the ground is 25% H2S. So that's fatal on a single breath. And in order to get the modules to this place, they had to build them very small to float on barges to go through canals, so everything is very compressed in terms of space. So again, huge human factors issues to actually build an asset that's going to work for the next 30 years. And these are the sorts of things that we get involved with integrating into the team of other specialist engineers and making sure that the human operators who are then handed this thing over can actually do their jobs safely and efficiently. There's also a mention for a website on offshore ergonomics. This is something we put together for the UK Health and Safety Executive over 10 years ago now, but it's still got a lot of relevant information in terms of existing assets and how you deal with some of the ergonomic problems that are there. So we're all aware of the sorts of challenges, human factors challenges we deal with, particularly in the oil and gas industry. Harsh environments. I always say when I go into design contractors' offices and see pictures of clear blue skies and flat seas, that this is not what you should be, the impression you should be giving to your young engineers who are designing the new generation of assets. You need to be putting pictures like this on the wall so that they understand what it's going to be actually like to operate these things in the sort of conditions that we encounter. Traditionally, challenges of poor layout have dogged us for years. I mean, you know, here's some examples in my probably many thousands of photographs that I've taken over the years of just basically poor design. You know, these are, in this case, manual valves. It's what I always say. What's the definition of a manual valve? Well, it's a valve you've got to be able to get a man to, or any other operator. You know, well, if that's the case, well, design it so you can actually get that access. Otherwise, it just becomes a leak point that nobody can use. So it's a very simple and fundamental point, but something that we haven't necessarily done very well in the past. Accessibility. Here's a pump skid. Produce water skid, requires daily lube, oil and vibration checks, but there's absolutely no way that the operators can actually get in there and do those. So what happens is they don't happen, the performance degrades, it loses, and then when it fails, you can see to actually get those things out, you've got to shut down the plant. You know, you can't lift those things out without removing spool pieces and in the operating asset. So for the sake of some accessibility and design in the first place, you've now reduced your availability of your asset very considerably, as well as the safety issues associated with it. You know, things like human-machine interface design, again, extremely poor. You see those dials on the left. I mean, the only thing you can read on those is the name of the manufacturer, and that's probably the last thing I'd want to advertise with such a poorly designed dial. I mean, that one's one of my favorites because I was called to look at that, ask why the operators kept giving wrong readings when asked to give a reading on it. And so, well, it's pretty obvious to me, particularly in dark and dirty conditions, which is how this is used. The wrong end of the needle is easier to see than the right end of the needle. So, you know, why would you possibly want to design a display like that? You know, we still have them. And, you know, here's one of my favorites in terms of, you know, poor control design. Anybody spot the problem with that one? Can anybody see what the issue is? Somebody tell me? Yeah, absolutely. Yeah, look at the bottom left. So it's a different way around from the other three. So what happens? Yeah. In this case, it's not a safety critical one, but it's a production critical error here, and process upsets occur because the ops are closing instead of opening. But yeah, you're going to do that with this layout, aren't you? You know, it's not a matter of retraining the operator, of telling them to be more careful. They're just doing what people do. So we've got to design it to make sure that it's hard to get it wrong and easy to get it right. And providing things like this and expecting them a bit of training to never make a mistake again is never going to work. This is human factors in practice. And also one of my favourites, I can't do a presentation without putting this slide on, in terms of unintended consequences of signage. I think you can see what's going on there. That actually meets the specification for having no smoking in red on one level and safety first in black on another level, but I think the way it's implemented has created the opportunity for the wrong information. Anyway, let me race on now to talking about how we actually get the design right in projects, how we actually integrate human factors throughout a project. The first thing to say is it's the human factors needs to fit into the way the project actually works, and that's what we've been at pains to develop over the years. You know, we fit in to the engineering approach, which is largely based around specifications, and that's what the way you know, the driving force for most projects. And it's about treating human factors as just another engineering discipline in a project. You know, we're there to get the best performance and reliability out of the human part of the system. Your plant is not going to work without pumps and pipes and rotating equipment and vessels. You have specialist engineers to look after all of those parts of the system. Neither is it going to work without humans, and therefore you need a specialist engineer to get the best performance and reliability out of the human part of the system. Because if you don't, you're not going to get that performance and reliability. Why would you not have a rotating equipment engineer on a project? You wouldn't dream, or a C&I engineer on a project. You wouldn't dream of doing that. But many projects still don't have a human factors engineer. Well, why not? You know, you're just ignoring a very fundamental part of the system and expecting it to work without a specialist engineer to get the best performance out of it. So that's an important message to take forward. There's two main areas of work that we cover in a project. One would be about the plant and equipment layout, the sort of pictures I've just shown you, getting accessibility, operability right, is one aspect of it. But the other, and equally important part of it, is dealing with the human contributions to major accident risks. It's about understanding where the human can actually add safety to the system and where the human actually adds vulnerability to the system, and how we actually deal with that and use human characteristics to their best advantage and cover for human vulnerabilities is what that part of the process is all about. Right, but I'll come on to that a bit more in a minute. So in terms of actually how we go about integrating human factors into a project, well, the way we used to do it, for probably the first 10 years of my career in oil and gas, I was invited along late in a project to have a look at what they'd already designed. And, you know, so typically wheeled in at the 60% model phase stage and asked to make some comments. And, you know, normally those comments would be, well, you've got lots of problems. There's lots of things here which are not right, are not going to work, either difficult to use or unsafe. And, you know, I suggest you change them. Well, it's too late. You know, we can't do anything now. So both parties go away saying, well, that was a waste of time, wasn't it? You know, we've spent some money, we haven't really gained anything. But, you know, now finally it's been understood that that's not the right way to do it. Now what we do is we integrate human factors in the project all the way through. Starting from the beginning, we front-end load it. We have a human factors program from concept right through to operate phase, and just like you would any other discipline engineer on the project. We specify the human factors requirements right at the beginning of feed. Then we know produce that into a specification document, then the rest of the project can be getting on with it, designing it in from a fundamental basis without actually just doing something and then asking us afterwards if it's okay. Well, as long as you follow the spec, then it will be okay. But we need to make sure that right spec is in place. Now, when we attend model reviews, it's just to check that the human factor specification is being complied with. This is quite a powerful tool, particularly when you're dealing with vendor supplied items as well, who are notorious for ignoring specifications and providing us with inaccessible and hard to use equipment. If you provide a human factor specification as an input document at the bidding phase, then they know at the beginning. You're not going to have inaccessible valves. You're not going to have unreadable displays on this skid package that you're going to provide us, because if you do, it'll be out of spec and you'll have to fix it at your cost. So, you know, rather than creating problems for the project by identifying the human factors issues, it helps to put the problem back to our vendors and get them to perform better for us. Now, there's reasonably, a model that the industry has developed for human factors integration, produced by the OGP, now the IOGP, on human factors engineering projects. What this provides is really a guide on how to do it, the stages of the process. It gives roles and responsibilities, competencies, the activities in different project phases and the deliverables, sets out a route map of what you should be doing and what the deliverable should be at the different phases of the project. And this has now become pretty much the industry standard. And most of the major operating companies, Shell, BP, Conoco, Chevron, a number of others, Statoil, are now following this model for their internal processes and standards for human factors integration. You know, here's an example of a route map from one of the operating companies that have basically interpreted the IOGP model and created a model that works for them. So some of the key activities, for probably the three most important points out of human factors in the project are these: the screening, creating the plan, and then providing the human factor specification. So the screening is something you do very early. You do beginning of feed if you can, and that sets out the human factors drivers, issues and risks for the project. Then you know, well, if this is a project where it's not very different, there's not much new, it's not terribly hazardous, it's all very familiar, we've done it before many times, you don't need a big human factors program for it. But if it is new, big, different, hazardous, brand new technology, a different manning philosophy, all those sorts of things, then yes, you're going to need a lot more human factors. And if you identify those things right up front, then you've got a plan that's fit for purpose and will meet the needs through the project. Thank you. You've got, so then from the screening, you create the strategy and the plan. And the next thing you do is to create the specification document. So again, that's done early. It will be published in a project as an engineering document alongside any other specification. It brings together all of the main human factors requirements for the project. And those will depend on where it is in the world, what the regulations are, who the end users are going to be. It's going to be different for Dutchmen than it is for Filipinos in terms of sizes and spaces. You can't have a single standard for accessibility to meet the whole world's population. It needs to be specific. It also needs to meet particular regulations. So the specification is a very important document, but one size won't fit all. You then release that into the project. It then gets used as an input document by the other discipline engineers, and they'll happily go about their job implementing this in a normal and natural way without lots of extra checking. So, the spec will typically include these sorts of things and will be put together in a very visual way so that it's very user-friendly and easy to follow, and is a document that is fundamental not only in the sort of as an input to design, but also in validation and model reviews, etc. Another area, valve criticality analysis. How do we get those valves in a place where people can access them? Well, processes go through to prioritize in terms of importance and frequency and criticality. You get the important valves in the accessible places. The ones that are rarely used are not important. You don't need to provide access to. So rather than adding weight, this process saves weight and saves cost and saves time. So if you go through this properly at the beginning of the project, put the valve criticality in your P&IDs before you give it to your piping and layout people, then they know where they've got category 1 valves. They've got to bring those together on a platform. Where they've got category 3 valves, they don't have to worry about access. You've got a much better designed plant from the very beginning. You don't have to go around adding platforms and ladders later on because you found stuff that's not accessible. So in my 2 minutes now left, I'll talk very quickly about the human contributions to major accident risks. Well, this is about where, really humans are blamed for major accidents. This is one I just found off the internet. A boat sinks, human error is blamed, 12 fatalities, total loss of the asset, and it says there, as you can see, in the middle paragraph, a valve that to cool the engine had been left open overnight. So a simple task, the omission of a simple task caused a major loss of the asset, a major loss of life and total loss of the asset. Well, that's a simple task, but it's a critical task. It's what we'd call a safety critical task. And safety critical task is a way of identifying situations where simple errors can have catastrophic consequences. And that needs to be built into the project. And it can be done so from the very beginning. Don't rely on people not making mistakes to keep your asset safe, because if that's what you're relying on, it's not going to be safe, and one day it's going to go wrong. We can do better than that. We can identify where the critical tasks are, where the human vulnerabilities are, and we can provide additional safeguards for those. But there's a process to go through. Because I'm running short on time, I won't go through all the slides I've got to sort of explain that, but it's here we're talking about critical tasks which are at a major accident level. So it's not about personal injury safety critical tasks, it's about major accident hazard critical tasks. So things if the operator gets it wrong, it can have a very poor consequence. You can do this in a project. There are ways to actually identify tasks by looking at things like HAZOP and bow tie, identifying where you've got the human as a safeguard to a significant risk, and start then either designing the people out. I won't go through the HAZOP example here because we're running out of time, but basically what that little part shows you is that when we're trying to put engineering safeguards alongside human safeguards, they're very different. The sort of failure on demand, the reliability level for humans versus engineering safeguards in a system, you've got at least 2 orders of magnitude less in terms of reliability. So whilst you might have a high pressure trip or high or PSV or whatever as your engineering safeguard, if you've also got a safeguard as a procedure, a response to an alarm, etc., then you can't put the two next to each other. You know, they're 2 orders of magnitude different in terms of their reliability. And that's what you need to remember. And that's just a simple characteristic of human beings. So, you know, don't try to think that you can train people and give them procedures to be 100% reliable. It's never going to happen. What you do need to do is to have humans in the loop where they're going to add value, and their flexibility will actually you know, provide a safer system or more efficient system than endless amounts of instrumentation and engineering control. Okay, so let me just go on to my last slide then. So success factors for integrating human factors into projects. Well, first of all, it's about integration, not review. So be involved all the way through, be involved early, align with the engineering activities and processes, focus the human factors effort where it adds most value, which is about improving the design. And the human factors deliverables need to be put in the same sort of format as any other engineering deliverable. It's not HS study reports, it's about specifications and improvements to the design. So hopefully you're not too far over. Thank you very much for your time and attention.